today's graduating bits session. It's the second of ITCS. We had one yesterday as well. If you're not familiar, graduating bits is an exciting tradition at ITCS in order to highlight some of the individuals who are near graduation, one way or the other, really highlighting some of the outstanding young members of the TCS community here. So today we're going to have a series of 11 lightning talks in a row, each about 4 minutes long, and yeah, we'll just jump right into it. The first lightning talk for graduating bits will be given by Sarah Scheffler at Princeton, and Sarah, feel free to take it away whenever you're ready.
All right. So good morning, I'm Sarah Scheffler. I'm currently a postdoc at the Center for Information Technology Policy at Princeton. My background's in cryptography. I got my PhD last year from Boston University, advised by my Uncle. And I'm looking for tenure track positions after my current postdoc is completed. So my research is a mix of applied cryptography and some interdisciplinary law and computer science work. My applied crypto work is primarily in zero knowledge, and that's all fairly standard stuff. So I'd like to spend most of my time talking about my interdisciplinary law and CS work. So I'm going to describe two projects in more detail, one that's mostly completed and another that's currently ongoing. So the first work in this area I'd like to discuss is about compelled decryption in the US. So this is when a court orders someone to decrypt their device, usually by entering their passcode. So why do we as cryptographers think we should have any say over what the interpretation of the law should be in this area? Well, there's currently no consensus among courts and legal scholars as to whether or not the government can compel people to decrypt like this. So the underlying legal doctrine was formulated to determine when people can be compelled to produce things like tax documents. It has to do with what is learned by the government when someone is compelled to do an order that might have implicit testimony. And we actually think our definitions of knowledge and learning and leakage that we use in cryptography are actually a very helpful tool to add to the toolbox to answer this specific question. So I'm not going to get too into the details, but under this doctrine, the government can compel you to do things it could have done without your help based on what it already knows, but it cannot compel things that it could potentially only learn from your mind, because this would violate the Fifth Amendment. So we notice that this concept is very similar to the cryptographic concept of a simulator. So you can figure out if the government is relying on leaked testimony by figuring out whether or not it can simulate the results without using the respondent's mind, but using everything else in the world. So we use this concept to analyze several scenarios, both involving encryption and not. When we apply this method to compelled decryption, we find that the government cannot compel decryption in the general case, but this changes with the presence of additional evidence that does often exist in real-world settings. We also introduce an idea called FC resilience, which is a security property of a crypto system that basically asks if its user can be compelled to reveal the secrets used in that crypto system. That's not the end of the story, but I also want to describe some other ongoing work about content moderation in end-to-end encryption, which I know is a tricky subject. In fact, content moderation is tricky even sort of in the ideal condition, right? Even so we have constant arguments over what we should and shouldn't do with all sorts of categories of content. And even when there's broad support for removing a certain kind of content or even a law mandating it, this is still a really, really complicated, difficult issue. And the question becomes even more challenging in the end-to-end encrypted setting. And so it's reasonable to ask, technically speaking, what sorts of properties can we achieve here? Like what sorts of moderation can you still even achieve under encryption? And then also policy-wise, what are the pitfalls here? And these two questions reinforce each other. So one part of this work is a survey of existing approaches to handling this in end-to-end encryption. Another part of this work is to explicitly dig into the policy analysis. And the encrypted setting really does pose policy challenges above and beyond those in standard content moderation. And like I said, even normal content moderation isn't exactly a walk in the park as far as policy goes. And then that analysis allows us to ask if any of the myriad policy problems that we sort of come up with can be addressed cryptographically. So we built 3 protocols. We built one signature scheme to create a root of trust for the ban list. We created an MPC protocol to ensure that users eventually get notified of detections, and one zero knowledge proof that allows a deployer to show that a specific image is not banned. So this is a summary of everything that I've worked on over the course of my PhD and postdoc. I encourage taking a screenshot before I get cut off here. I've put my email in the upper right-hand corner. So please feel free to contact me for any reason, whether it's job related or you just want to chat about this kind of work. Thank you.
Perfect. Thanks, Sarah. Yeah, you're perfect on time. Next up, we'll go to Gavin Brown at Boston University. Gavin, whenever you're ready, feel free to take it away.
All right, hello. My name is Gavin Brown. I'm a fifth-year PhD student working in privacy and machine learning, advised by Adam Smith. After graduation, I hope to complete a postdoc and obtain a tenure-track faculty position. In our world of ubiquitous data analysis, we have serious concerns for privacy. For instance, in this XKCD comic, the revolution is foiled by autocomplete. More mundanely, however, I might be concerned that my medical diagnosis will become public if I participate in a study, or that participating in the census will reveal that I'm violating zoning or immigration laws. These concerns can be formally addressed by asking the following question, which I view as one of the central question of my PhD, which is, what does an algorithm's output reveal about an individual's data? Some of my work focuses on designing algorithms within the framework of differential privacy, which provides a formal constraint on how much an algorithm can reveal about its input. A recent NeurIPS Spotlight paper with collaborators at BU and Northeastern tackles high dimensional mean estimation of Gaussian distributions under differential privacy. The task here is to estimate from data the mean of a Gaussian distribution with unknown covariance under differential privacy, which informally means that just the similar data sets must have similar output distributions for the algorithm. Prior work suffered from problems requiring prior knowledge on the covariance matrix or higher sample complexity than the empirical non-private mean estimator. We provide two differentially private algorithms that compete with the non-private baseline in terms of sample complexity. The first is a modification of the Gaussian mechanism, and the second is a modification of the exponential mechanism run over Tukey depth. I like these two approaches for different reasons. The first takes a canonical tool, the Gaussian mechanism, and extends it beyond the basic clip-in noise paradigm. And the second builds on tools from outside differential privacy, in this case, robust statistics, another field that formally models how changing a few data points can affect the output of the learning algorithm. I'm interested in exploring the connections between these two areas. Outside the framework of DP, recent work with collaborators at BU and Apple demonstrated simple learning tasks where accurate learners must memorize entire training examples. In other words, the model must somehow encode a large fraction of the data it receives. A result even captures memorization of irrelevant data, information that's unique to the data set and useless for classification. Our results require new information complexity lower bounds for communication games related to the learning tasks we propose. To supplement our theorems, we also have experiments demonstrating strong reconstruction attacks against simple models, showing how that they directly encode a large fraction of their training data. Looking forward, I believe we have only scratched the surface of this memorization phenomenon, and I'm excited to understand it in more depth. In particular, we have forthcoming work with similar results in a streaming setting. And our results have implications beyond just privacy, since our mutual information lower bounds imply space usage requirements. In summary, my research motivation can be written down in two questions. Why do complex learning algorithms sometimes encode large amounts of information about their inputs? And how can we, as algorithm designers, avoid this bad behavior? Thank you for listening. You can find links to these and other papers on my website, which is also linked from the program.
Thanks, Gavin. Perfect timing. Wow. Yeah, next up, we have Chen Wang at Rutgers. Chen, feel free to start whenever you're ready.
My screen, actually?
Yeah, I can see your screen just fine.
Okay.
Go ahead.
Let's get started. So hi everyone, I'm Chen Wang from Rutgers. So today I'm going to talk about a little bit about myself and my research on scalable machine learning with sublinear algorithms. So I'm a fourth-year PhD student at Rutgers, advised by Sepra Asadi. So I will be on the job market soon, as early as next year, and I'm also looking for research internship like this year. Okay. So my research interest, broadly speaking, is in the intersections between machine learning and TCS. This is a broad subset of things, some topics more computational, some topics more statistical. So today I'm going to emphasize on my work for machine learning with sublinear algorithms. So the context is that, so in the past decades, we have these numerous breakthroughs on moderate size machine learning. We have these like novel models like every year, but there's a challenge of learning with massive data sets. So what do I mean with massive data sets? If you are familiar with this like machine learning benchmarking data set, you know that for imaging machine learning is usually like few thousand to like 10 to the 6 or 10 to the 7. And graphing machine learning experiments usually use few thousand to few 100,000 nodes. On the other hand, for like many applications like in Google or Amazon, they have like this online retelling of 350 million listed products, or some snap graph like 10 to the 7th vertices and 10 to the 10 edges, okay? So this makes the aforementioned model not like actually applicable. So the challenge here is how to learn from massive data sets when reading or storing the entire input is impossible. And we tackle this by sublinear algorithms. So we realize that in classical algorithm setting, we first read and store the input and then do something. But in sublinear algorithm, we work with resources even smaller than the time or space itself, than the input itself, okay? So for example, if I give you a graph that has many edges, okay, in some linear time algorithm, I only read the red edges. I don't care about the other edges and solve the problem. And for a sublinear space streaming algorithm, I have a memory that is potentially smaller than the stream itself. So I only store like very small subset of things. So I want to highlight two of the results on this front. The first one is streaming exploration. Our paper is Doc 20. So we studied this classical pure exploration in multi-arm bandits. We give n arms following the Bernoulli distribution, and we want to find the most rewarding arm, which is the arm with the highest probability to give the reward. Okay. So the optimal sample complexity has been known for almost 20 years, but it is like an n-arm memory. And we introduced a streaming model, and therefore this problem to study the space efficiency. And our result shows that there exists an algorithm finds the best arm with high probability using the optimal sample complexity in a single arm. Okay, so I quite like this result because it somehow shows there's no space sample trade-off in such an exploration problem. And the second example on this front is a paper on this conference, study the correlation clustering with the disagreement minimization objective. Okay, so prior to our result, best known result is the serial approximation with the absolute n square additive error in order of n or absolute square time for sublinear time, and the constant approximation with multiple passes over the stream for the sublinear space. Okay, so we managed to modify this with the constant approximation in O to the end of time, and also we show that there also with a similar technique there is a constant approximation in a single pass for the data stream. Okay. So again, I'll be graduating soon, and I'm looking for a internship also. And thank you for your attention.
Perfect. Yeah, thanks so much, Chen. This was great. We're good on time. Next up is Damalika Mukherjee at Purdue. Damalika, you can feel free to share screen and start whenever you feel ready.
Okay, thank you. Let's see. Okay, so this is a really good lineup because my work is actually in the intersection of the two previous topics. So I'm Damalika. I am advised by Elena Brescu and Jeremiah Blocky at Purdue. I'm graduating next May, and I'll be looking for a postdoc then. So I want to focus on my current work, which is on differentially private sublinear algorithms. So as was mentioned previously, I'll just give a motivation. So here we say you have like company X that has massive data sets, and they want to run some algorithm to gather some aggregate statistics about the users. And they want to use the output of this algorithm to target some population with their product. So in these scenarios, you want polynomial time algorithms may not be fast enough, so you want sublinear algorithms. And you also want to, say you also want to preserve the privacy of the users in your data sets. So for example, you don't want the output of this algorithm A to expose like user 1, for example. The question that we ask in this motivating example is, is there a way for companies to efficiently gather information, but also preserve privacy of individuals in the data sets? So this is where differential privacy comes in. As I was explained before, differential privacy guarantees that you will not be affected adversely or otherwise by allowing your data to be used in any study or analysis, no matter what other data sets are available. So this notion is a gold standard in privacy. It solves problems that's faced by anonymizing data, and it also gives you provable guarantees on privacy. So my work so far in this has been showing the first results in clustering for that lies in the intersection of being differentially private and also running in sublinear time. I also have another work that is coming soon that gives the first results in estimating graph parameters in sublinear time and in a differentially private manner. I previously have also worked on topics in cryptography. So these are some of the papers that I've been a part of. And yeah, this is a pretty short presentation. So yeah, I'm graduating next May, and I'm happy to talk to anyone who's interested in these works. And I'm looking for collaborations this year.
Perfect. Yeah, this is well under time, Damalika. Thanks for that. Out of curiosity, what can you say? What sort of graph parameters you try to estimate?
Yeah, we have results for estimating the size of maximum matching and average degree of a graph and size of vertex cover.
Cool. Yeah. All right. Nice. Thanks, Damalika. Next up is Wanrong Zhang. Wanrong is at Harvard. Please feel free to start whenever you feel ready, Wanrong. Wanrong, are you there?
Yes, I'm here.
Cool.
I'm
Yep.
going to share my slide.
Yeah.
Can you see my screen?
I can see an empty screen right now.
Hmm.
Yeah, okay, now we can see your slides. Perfect. Go ahead whenever you feel ready.
Hello, everyone. My name is Wanrong Zhang, and I'm currently a postdoc at Harvard. And previously, I got my PhD from Georgia Tech, and I'm looking for tenure-track faculty positions starting from this fall. My research focuses on the theory and practice of data privacy. As we have already seen in previous talk, the field of differential privacy offers data analysis tools and provide powerful worst-case privacy guarantees. And the bulk of my work has been focused on privacy-preserving statistical tools for the statistical online decision-making problems. And the second part focuses on the dataset leakage properties and protection, because differential privacy only guarantees the individual level privacy, but it doesn't aim to protect some population level information, such as the distribution of race and gender among users in the trained data set or some other proprietary information. We gave a text showing this machine learning model can unintentionally memorize such information and it causes leakage. And we also provide methods to against those attacks, including a new privacy notion and mechanisms to achieve that. And in an ongoing work, I'm also interested in the composition theory of differential privacy, specifically the concurrent composition. And today I'd like to briefly talk about my work on the attribute privacy and the concurrent composition. So attribute privacy protects the global properties of sensitive attributes in the dataset from leaking during analysis. So for those of you who are familiar with differential privacy, we are used to think about the privacy at the individual level, corresponding to the roles of a database. And in this work, we instead consider privacy of the attributes or columns of a database. Then as we take the view of the database owner who wishes to publish aggregate information about her datasets, but also want to protect some like global information, like aggregate information in certain columns. For example, in this case, the average SAT score, we know that SAT score are correlated with sensitive attributes such as race, gender, and socioeconomic status. But we wish to hide the average parent income, whether it's greater than 90K or not. And in this paper, we provide a framework and mechanisms to achieve attribute privacy. And another interesting problem I'm currently doing is concurrent composition of private mechanisms. And the previous work of composition theory focused on the non-interactive mechanism, but interactive mechanisms are needed to capture many of the intended application, like for example, when queries are correlated. And specifically, we consider the concurrent composition. As a motivating example, suppose we have a differentially private query system, and I set a server to answer query with privacy budget epsilon, and you also set a server to answer the query with epsilon. And the reverse, we can do concurrent attack to such systems. And how do we account for the total privacy loss? So right now, there's only one work that gives the composition theory for the pure DP and approximate DP. And our result gives a concurrent composition theory for the more general privacy notion, the FDP. Thank you for listening. And again, here's my website, and you can find the details of my papers here. Thank you.
Perfect. Thanks a lot, Wanrong. Next up is Xuangui Huang at Northeastern University. Xuangui, feel free to share screen and start whenever you feel ready.
Okay. Can you see the screen?
Yeah, looks great. Feel free to start whenever.
Cool. Hi, everyone. I'm Xuangui Huang from Northeastern. I'm working with my advisor, Manu Viola, on circuit complexity, pseudo-randomness, and data structural robots. I plan to graduate next year, and I'm looking for an industrial research job. My current research centers around the power of constant depth circuits. It is well known that parity function cannot be computed by AC0, the constant depth Boolean circuits. We therefore enhance it by adding unlayered parities at the bottom. Recently, together with my advisor Manu and another PhD student, I gave a general template to construct affine extractors, which is an important class of distributions in pseudo-randomness. Using this template, we show that we only need depth 4 and almost quadratic size to compute a good affine extractor. It is also well known that majority is not in AC0. So another way of enhancing it is to allow majority gains. My result in 2020 showcase its power in the sense that using TC0 reductions, we can reduce the problem of solving general linear systems into the problem of solving some very specially structured linear systems. And a closely related topic is matrix rigidity. Together with Manu, we construct explicit functions that is extremely rigid, using techniques like rectangular PCP and the famous gas and stat framework. And another closely related topic is descriptive complexity by the famous connection between first order logic and AC0 circuits. And we show that the parameterized version of vertex cover can be defined with very little resources. And that's all. I'm Xuangui Huang, looking for industrial research job next year. Thank you.
Thanks, Xuangui. That was a very efficient talk. Cool. Next up, we have Ziv Scully at CMU. Ziv, you can feel free to share and start whenever you feel ready.
Okay. Everything appears in order.
Yep, go
okay.
ahead.
All right. Hi, everyone. I'm Ziv. I'm a PhD student at Carnegie Mellon, graduating soon, looking for an academic position. So I like to hand draw my slides. And on this slide, you'll see a few of the logos from title slides of previous talks of mine. And if you're curious what this bar of soap in a wine glass is doing, you can come to my ITCS talk later today. Okay, so at a high level, my research and my interests are thinking about performance under uncertainty. And performance means lots of different things in different contexts. And my work is focused on the specific aspect of delay, specifically in scheduling and queues. And this is an important aspect of performance because it keeps showing up. So all sorts of situations in your daily life, in computer systems, you get delays. And so how do we reduce delays? Well, we could acquire more resources or we could invent faster algorithms, but that takes time and effort and money. And something we can do with what we already have is we can change how we schedule. And this can really reduce delay, but the theory of scheduling is pretty underdeveloped compared to what's happening in practice. So I mentioned uncertainty earlier. So something that happens in practice is jobs come in, but you don't know the resource requirements of those jobs. So how should you schedule under that type of uncertainty? So both in, this might be the amount of time jobs take, also things like the number of servers a job might occupy. So another, speaking of multiple servers, multi-server systems are really hard to analyze from a theoretical perspective, even when you use very simple scheduling policies like first come, first serve. And then a final aspect that's difficult to attack from a theoretical perspective is preemption practicalities. It's often helpful when scheduling to interrupt a job and then start serving a different one. But theory usually doesn't account for limitations on when this can happen or overheads. And so in my work, I develop new theoretical tools that help us attack these sorts of problems. And I'll mention that some of these have been open for decades in queuing theory. And so our tools give us the first results in some of these spaces. And so let me tell you about two of these tools. Let's open up the toolbox. So the first tool is called SOAP. It's a new unifying theory of single server scheduling. It unifies not all, but lots of what was previously known about scheduling in a single server queue. And in addition to unifying, it generalizes. It greatly increases the number and variety of policies that we can have. So that's the first tool. The second tool is called Wine. Wine is a new queuing identity that's in the tradition of Little's law, which is this kind of famous result from queuing that sort of relates the number of jobs in the system to the system's delay. And so we come up with a sort of new friend for Little's law that helps us reduce the analyses of complex systems to the analyses of related simple systems. And so we've used SOAP to study system. We've used SOAP and Wine both in multiple contexts. And the one I'll highlight here is this noisy size estimates. This is scheduling when you only have a partial information about how long a job takes. This is what we do. This is the work from ITCS. And I'm excited about it because it uses both of these tools. So zooming out where I might like to go in the future, I'd like to think about other aspects of performance under uncertainty. So some work I've done in this space is I've done some work on combinatorial optimization under uncertainty that appeared at IPCO. And then more generally, I'm interested in thinking about algorithms with predictions. My ITCS work has a bit of that flavor and other kind of aspects of optimization under uncertainty. All right, and with that, I'll conclude. Thanks.
Thanks, Eve. Yeah, I really like the drawings. I also like your hook about what SOAP and Wine is, though you kind of gave away the suspense here, but they should go to your talk nonetheless. Next up is Lijia Chen, who's at MIT. Lijia, feel free to share and go whenever you're ready.
Can I see the screen?
Yeah, perfect.
Yeah, so hello everyone, I'm Lijia Chen. I'm currently a fifth-year PhD student at MIT, and I'm advised by Professor Ryan Williams. And I'll be graduating in this summer, and after that, I'll be joining UC Berkeley, and I'll be looking for a faculty position after the postdoc. So I maintain a very broad interest in theoretical computer science, and my work has spanned many different areas. Today, I'm only going to focus on computational complexity theory because that's my major focus right now. And you can find some summaries of my other work on my personal website as well. My work in computational complex theory can be categorized into 3 lines. The first line of work is on getting optimal generalization for harness assumptions. So here we show that one can essentially get rid of all the randomness without paying any cost at all. My second line of my work is on the algorithmic approach to circuit level bounds, which is proposed by my advisor, Ryan Williams. In this line of work, my co-authors and I use sophisticated PCT constructions and many other ideas to prove new circuit level bounds. Those work include some new constructions of rigid matrices, the first strong average case lower bounds against ACC0, and the first almost everywhere circuit lower bounds against ACC0. So here, ACC0 is a frontier circuit class in complexity theory for which we all knowledge is very limited. So this work gives us more understanding into this frontier class. The last line of my work is on harness magnification. So roughly speaking, here we prove in a formal sense that breakthrough results such as P not equal to NP is just 1 epsilon away from what we can currently prove. So maybe we are not that far away from proving those breakthrough results. So next, I will talk a bit more on my line of my work on generalization. So here, the motivating question is, what's the fastest possible generalization of T of n time randomized algorithm? Here, we use BP time 12n to denote all problems solvable in randomized 12n time. And in other words, we want a general transformation which can convert any 12n time randomized algorithm into equivalent deterministic algorithm, which are as fast as possible. The classical line of work shows that one can de-randomize 12n time randomized algorithm with a polynomial overhead, but unfortunately, the exponent is very large, like 7. There's a recent work improving this to quadratic. So in my recent two works with Roy et al., we proved that under plausible harness assumptions, first 12n time randomized algorithm can be de-randomized with only an overhead of n, and this overhead of n is optimal. Second, we can further de-randomize 12n time randomized algorithm with essentially no overhead, and no polynomial time adversary can find a mistake. So here, it's not a perfect generalization because the deterministic algorithm can still make mistakes. But the catch is that no one can find a mistake. So this makes it not subject to the optimality of n mentioned above, and it's still very useful in the practice. Finally, on the technical side, we prove that no black box generalization algorithm like PRGs can achieve our second result. So in fact, we propose a new framework for non-black box generalization to achieve our second result. Yeah, that's all. Thanks.
Perfect. Thanks a lot, Ligia. Next up is Yazamin Nazari at University of Salzburg.
Okay, you see my slides, right?
Yep, everything's perfect.
Great. So yeah, I am Yazamin. I am a postdoc at the University of Salzburg in Austria now. I work with Sebastian Förster. And before that, I finished my PhD in Johns Hopkins University, where I worked with Mike Dinitz. So let me start by saying that I will be on academic job market for tenure track jobs soon. I will also be open to related industry research positions. And let me do the reverse thing here and say that we also have a postdoc opening in Salzburg. And it's going to be on graph algorithms, and there are a lot of nice mountains here, so join. Okay, so my research is, whenever I figure out how to go next, okay, mostly on graph algorithms and various computation models. I'm going to get into these in a moment. And I also sometimes think about approximation algorithms and online algorithms. But during my PhD, I mainly focused on distances in graphs, and in particular, distance objects such as hop sets, spanners, emulators, distance oracles. And at a high level, for these objects, we are given a graph G, and we want to store some information about distances that trade off some different factors in the original graph. For example, in case of hop sets, we want to trade off the number of hops on the shortest paths with the accuracy of the distances. And the other objects here are distance sparsifiers, where they trade off the accuracy with the number of edges in this subgraph or a data structure that they store. Okay, so one of the models that I've recently been focusing on is dynamic algorithms, where the input changes over time. So in case of graphs, the graphs change, edges can be deleted or inserted or both. And two of my recent work are on computing the objects I mentioned and using them for computing the distances in delete-only dynamic models or fully dynamic model. And I also worked a bit on distributed and parallel algorithms. Roughly speaking, distributed models are models in which we need to run an algorithm on a network of sorts with some different restrictions. And depending on the type of restriction, we're going to have a different distributed model, like local, congested clique. Not going to get into details of those. I also taught about the massively parallel computation model, which is something between the classic parallel models and these distributed models. And basically, during my PhD, I worked on understanding the objects that I described in these models and applying them for computing shortest paths and in some cases for optimization purposes. I've also worked on some other models. I'm going to present a talk in ITCS today about vertex fault tolerant emulators, where the goal is to construct emulators that can tolerate a certain number of vertex faults. I've also worked on like classical approximation algorithms, and during an internship, I worked on line matching. And just, I want to finish by saying that I would like to, in future, move more toward optimization, combinatorial optimization problems in distributed and dynamic models, and would also like to think about this existential distance objects, because I think there's still a lot of interesting open problems. And that's it. Please reach out if you have any questions and comments.
Perfect. Thanks, Yasamin. Next up is Raghavendra Adanki at UMass Amherst. Raghavendra, please feel free to share and take it away whenever you feel ready.
So the other participant is sharing the screen.
All right, you should be good now.
Yeah. Yes. Are you able to see my screen?
Yep, loud and clear. Now, not anymore.
Sorry, just a second.
Yep. Cool, we're good again now.
Okay, thanks. Hi, everyone. I'm Raghavendra Adanki. I'm a final year PhD student at UMass Amherst, where I'm co-advised by Andrew McGregor and Cameron Musko. Currently, I'm looking for postdoc or industry research positions starting in the summer. Broadly, my research contributions can be categorized into two themes. In the first one, I've worked on problems related to causal inference. Here, I've worked on fundamental problems such as causal discovery and causal effect estimation. Causal discovery basically deals with the problem of learning the causal graph, and effect estimation deals with learning the causal effect of between two variables. Here, I've also studied approximately learning causal graphs, distributed algorithms for learning causal graphs, and my results have appeared in recent machine learning conferences. The other major theme of my research is modern algorithms, that is algorithms for current day systems. Here I've studied various problems such as maximizing diversity under fairness constraints, how to deal with noise by designing robust algorithms which are also query optimal, how to design sublinear or dynamic algorithms with changing input, and also search result diversification in information retrieval. I'll briefly touch upon one of the results in each of them. So in causal discovery, the goal is to learn the causal graphs. By this, I mean, we are given a set of variables. These can be thought of as nodes in a graph, and we want to identify the links between them. These are usually directed links, and the goal is to learn a directed acyclic graph. Here's an example of a causal graph, which is shown on the right side. Under certain assumptions, for the sake of this talk, I will not go into them. One can change the problem into a more discrete optimization space by first detecting the presence of a causal edge, which is shown in the middle, like where we have detected that there is a causal edge, but we now have to recover the causal direction. To this, we use a fundamental primitive, which is known as an intervention, which where if we intervene on a subset of vertices, it'll allow us to learn all the directions of edges incident on it. Again, this is a great simplification, but this for the purpose of today, this suffices. So intervening on this S1 will help us recover the directions. Based on this observation, and we can devise a variety of objectives, and I've studied a few objectives, which is minimizing number of such sets, greatly improving on previous results, and devising distributed algorithms for minimizing these number of such sets to cover the graph. If there is a cost associated, I've given approximation algorithms and showed hardness results. All of these leverage interesting connections to theory in such as graph property testing, coloring, discrete optimization, etc. Finally, I'd like to briefly present a recent result, which is on sublinear time algorithms. Recently, we have seen a shift towards these global query models, which overcome the barriers of local query models in sublinear time. Local query model is an adjacency list or an adjacency matrix-based model. Here I've studied graph parameter estimation, where we focused on estimating number of edges or returning a uniform sample. And we have studied non-adaptive algorithms, where we ask all the queries at once before even looking at the graph. The query model which we focused on is this global query model of bipartite independent set, where we are interested in detecting the presence of an edge between the left and the right side. We've showed that just polylog queries for a relative error approximation of 1 plus minus epsilon is sufficient to estimate the number of edges. And that said, if you want to get in touch, here are my contact details. Thank you.
Thanks, Raghavendra. Next up, we'll have our last presenter of the session, which is Saurabh Patro at CWI. Subhashri, feel free to start whenever you're ready.
Yes, thank you. Let me see. Is this all visible?
Yes, yeah. Perfect.
Okay. Hi, I'm Subhashri Patro, and my PhD project has been mostly about quantum fine-grained complexity. I'm a PhD student at just a second. Yeah, QSoft, CWI. Like I'm employed by CWI and affiliated to University of Amsterdam. Okay. So let me briefly just talk about classical fine-grained complexity so that I can give an idea of what we are doing in the quantum setting. And so fine-grained complexity is mostly about understanding the hardness of problems within the complexity class P. So we would like to see, we know that in complexity class P, we have problems which are of n square complexity and cube complexity and things like that. But if we want to know hardness of a specific problem, we would actually like to know hardness of any specific problem. So for that, we do this fine-grained reductions, and that is, we conjecture a lower bound for some problem A, we reduce problem A to some problem B, and then we conclude a lower bound for problem B based on this believed lower bound for problem A. And in the classical world, lower bounds based on conjectured hardness of CNF SAT, 3-sum, APSP, orthogonal vectors are given. So to summarize, this is a picture from 2015, a survey article by Virginia V. Williams, but I'm sure most of, a lot more work would have been added here. And so in this, you can see that there are so many problems that whose lower bounds were conjectured based on 3-sum problem, CNF SAT problem or KSAT problem, and APSP problem. And we would like to understand how these problems behave in the quantum world. So in a pictorial way, like imagine we have these problems that are in this complexity class P, and we kind of have an idea of how hard they are in this world. Now we would like to understand how hard they are in this BQP land, where by BQP, I mean, it's a complexity class analogous to this complexity class P. Yeah, okay, so problems that require polynomial time in quantum world. And so we are like in my PhD, we started understanding these reductions, understanding how these hardness results were established for each of these problems. And we try to port those things, like put that information to the quantum world. And though in this picture, it seems very easy, but actually it was not a trivial task, and we had to go through a lot of blocks and things like that to do that. And meanwhile, there were other group by Aronson et al. Were also who introduced these conjectures in the quantum setting based on the CNF SAT problem. We continued our quest for understanding hardness or computational geometry problems, and based on hardness of these 3-sum problem in the quantum world, we gave more reductions, and our results were like very well accepted by this quantum community for us. And we expect that by 2003, that's when definitely, hopefully I'll graduate. We expect that we will have a lot more results and a lot more clarity on how these problems relate in the quantum setting with each other. Like to formally summarize my results up till now. So we first gave this variation of Seth conjecture in this quantum world. We called it the Q-Seth conjectures. So what is Seth conjecture? Seth conjecture says that the CNF-SAT problem requires 2 power n classical time. And a basic Q-Seth would be that CNF-SAT requires 2 power n by 2 quantum time, because we could use Grover and we could speed up this brute force thing. But what we noticed that like many reductions just become trivial, and some of them are not even tight. So we thought, okay, what are these reductions doing? And we noticed that these reductions were actually computing a more complicated property than just finding a satisfying assignment. And Grover speedups are not amenable for all of these properties. And we realized that like for some properties like parity and majority, even this Q-Seth, like even the CNF-SAT problem would take 2 power n quantum time. And based on these kind of observations, we concluded these non-trivial bounds for n power 1.5 for editors and LCS, which otherwise would have been just linear bounds if we would have taken this basic Q-Seth. And we also feel these tricks can be useful in proving lower bounds for many other problems, especially the string comparison problems. And but they will be the low-hanging fruit that we can explore. And after that, we also like tried to understand the hardness of three-sum problem in the quantum setting. And we looked at all these reductions from three-sum problem, these computational geometry problem especially. And most of these reductions were going through an intermediate step where the inputs were getting sorted. Now that is such a trivial thing in classical setting, but in the quantum world, it all would collapse because we don't have a fast algorithm to sort. So then we gave a non-trivial way to establish that your sorted threesome in quantum world also requires n time, just like threesome. And this reduction was the crux of our paper that we also presented at ITCS. The reduction went through a walk-based reduction, and that helped us establish hardness of sorted threesome. And consequently, we gave tight linear lower bounds for a lot of computational geometry problems. And this was also well accepted in the quantum community because we will be talking about it at QIP in March. I'm also currently working on some other problems right now, especially these lower bounds that can come from APSP, that is all pair shortest path problem. We have some work in progress, but we have not written it up yet, so it'll take a bit of time to for it to be online. But there are other two problems that I'm working on and which should be online soon. That is, we are giving some more tight bounds for some other computational geometry problems. And a slightly different area that I also have worked on is in the query complexity world, where we try to give relate quantum query complexity with decision tree complexity or some properties on these decision trees. Right? So this is about me. I'm expected to graduate early next year, and I'm looking for postdoc positions either in academia or in industry. So, thank you.
Perfect. Yeah, thanks a lot, Subhashri. And yeah, thank you to all the presenters today. I'm going to give everyone a little awkward round of applause sitting here alone by myself. But yeah, we had 11 great speakers today. Yesterday, we had another 14, so a total of 25 great young researchers who presented graduating bits. If you missed any of them, you can check out their recordings on YouTube. But yeah, thanks for joining. And the next session should be starting in about 10 minutes.
Thanks, everyone. And thanks for organizing this.